The CAP theorem, also known as Brewer's theorem, is a key principle in distributed systems, stating that it is impossible for a distributed system to simultaneously guarantee consistency, availability, and partition tolerance fully. A system can satisfy at most two of these three characteristics at the same time, but not all three. Consistency means that all nodes see the same data at the same time. That is, all read operations should retrieve the most recent write data. For example, if one node in the system receives a write operation, the system needs to ensure that all other nodes also receive this update in sync to maintain data consistency. Availability means that the system is always able to respond to read and write requests, even if some nodes fail. A system is considered available if it provides a non-error response to a request, although it may not guarantee the latest data. Partition tolerance refers to the system's ability to operate despite network partitions. When network issues arise and nodes cannot communicate with each other, the system can still function. In distributed systems, network partitions are unavoidable, making partition tolerance an essential feature for almost all distributed systems. According to the CAP theorem, no distributed system can simultaneously ensure consistency, availability, and partition tolerance. It can only satisfy two of these three properties. Since partition tolerance is almost essential in distributed systems, system designers typically face a trade-off, ensuring consistency and partition tolerance (CP) while sacrificing availability, ensuring availability and partition tolerance (AP) while sacrificing consistency. HBase is an example of a CP system, meaning it prioritizes consistency and partition tolerance. During network partitioning, HBase may reject certain requests to ensure data consistency is maintained once all nodes reconnect. For example, if a write operation occurs within a partition, HBase will ensure that all nodes reflect consistent data, even if some nodes become temporarily unavailable until the network is restored. Advantages: strong data consistency, with each read-write reflecting the latest data. Disadvantages: when network partitions occur, some nodes may be unavailable, reducing overall system availability. Cassandra is a typical AP system, prioritizing availability and partition tolerance. In case of a network partition, Cassandra continues to handle read-write operations without requiring all nodes to be in sync. When the partition ends, it reconciles inconsistencies in the background, achieving eventual consistency. Advantages: in large-scale distributed systems, even if some nodes lose connectivity, the system remains highly available. Disadvantages: reads may return outdated data until the system eventually reaches consistency. Traditional relational databases like MySQL typically ensure CA, consistency, and availability, but lack partition tolerance. Their design assumes reliable networking, allowing them to provide both data consistency and high availability. However, if a network partition occurs, the system may go offline entirely, ceasing to provide service. Advantages: strong consistency and high availability when no network partition occurs. Disadvantages: when network partitions or communication failures happen, the system may become entirely unavailable. In real-world distributed system design, developers often need to make trade-offs among the three CAP properties based on specific business requirements. Consistency. First, when data consistency is critical, such as in financial transaction systems, a CP system is often chosen to ensure that no inconsistencies arise even during network partitions or failures. Availability first. In systems with high availability demands, like social media platforms or streaming services, AP systems are preferred to maintain high availability, even if data may be temporarily inconsistent. Eventual consistency. To balance high availability with consistency, many systems, e.g. Dynamo Cassandra, adopt an eventual consistency model. This approach ensures that while the system remains highly available, all data will converge to a consistent state over time. This compromise is very common in distributed systems. Thanks for watching. For more information, please visit bowsy8.com. Designing a distributed cache is a crucial step in optimizing the performance of distributed systems. By implementing a distributed cache, you can reduce data access latency, alleviate database load, and enhance the system's scalability and response speed. Below, I will outline how to design a distributed cache system and briefly describe several common types of caching. In a distributed environment, data needs to be distributed across multiple nodes. To ensure that cache data is evenly distributed, consistent hashing is typically used to determine which cache node will store the data. This way, when the number of nodes changes, data redistribution can be minimized, maintaining the stability of the cache. Cache consistency is an important consideration when designing a distributed cache. In practice, cache consistency issues typically arise from two aspects. Write after read inconsistency. When the written data has not yet been updated in the cache, the read operation returns old data. Cache expiration mechanism. A time-to-live teach strategy can be used to automatically invalidate cache data after a certain period. Another option is to use active invalidation, such as notifying all nodes through a message queue. When using a distributed cache system, it is essential to ensure high availability and partition tolerance. If a cache node fails, the system should be able to automatically redirect requests to other cache nodes. Implementing replication mechanisms or deploying multiple data centers can enhance the system's fault tolerance. A distributed cache can incorporate a persistence mechanism to ensure that data is not lost if a cache node crashes. Three major types of caches. In the write-through strategy, write operations update both the cache and the underlying storage, such as a database, simultaneously. Advantages. Ensures strong consistency between the cache and the database, as each write is immediately updated in the database. Disadvantages. Performance can be poor because each write accesses the underlying storage, increasing write latency. In the write-back strategy, data is first written to the cache and the operation to write to the database is delayed. The cache system asynchronously writes the data in the cache back to the database in the background. Advantages: better performance, as write operations do not require accessing the database each time, resulting in faster writes. Batch writes can improve the efficiency of write operations to the database and reduce the frequency of small writes. Disadvantages: there is a risk of data loss since data may not be immediately written to the database. Data consistency can be poorer, as the system may read old data for a short period. Write-around is a variant of the write-through strategy. In the write-around strategy, write operations bypass the cache and write directly to the database, while read operations fetch data from the cache. Advantages: avoids the overhead of frequently writing to the cache, making it suitable for systems with fewer write operations. Works well for larger data sets, as it does not invalidate the cache due to frequent writes. Disadvantages: if the written data is frequently read afterward, the initial read request may miss the cache, leading to latency. High consistency requirements. For scenarios requiring strict data consistency, such as financial transactions or order processing systems, write-through is commonly used. This approach ensures that the system always provides the most up-to-date data when read. High performance requirements. For systems that require high write performance and can tolerate short periods of data inconsistency, such as logging systems or analytics systems, write-back is more suitable. By delaying writes, it reduces frequent small write operations, thus enhancing write throughput. Read-heavy scenarios. In systems with a high volume of read operations and fewer writes, write-around is a good choice. By avoiding frequent cache updates, it can improve read efficiency and reduce the maintenance burden on the cache. In distributed caching, it is important to address hotkey issues, where a single key is accessed frequently, leading to concentrated load on certain nodes and potentially causing performance bottlenecks. Common methods include request diversion, cache replicas of hot data on multiple nodes to distribute access requests. Local caching, store hot data in a local cache on the server to reduce load on the distributed cache system. Asynchronous processing, use asynchronous batch processing to reduce the frequency of hot data requests.
Thanks for watching. For more information, please visit bowsier.com.
Short polling, long polling, and WebSockets are different communication techniques used in web development to manage interactions between the server and client. Each of these approaches provides a solution for keeping the client updated with changes or new data from the server, but they operate in distinct ways, and each has its own advantages and disadvantages. Short polling is a method where the client periodically sends HTTP requests to the server to check for new data. The client sends these requests at fixed intervals, regardless of whether there is new data on the server. Each time the server receives a request, it immediately returns data, even if there hasn't been an update. Advantages: simple to implement with no special server-side optimizations required. It uses standard HTTP requests, making it highly compatible with all browsers and servers. Client-controlled. Developers can flexibly set the request interval. Disadvantages: inefficient performance. Frequent HTTP requests consume bandwidth and resources, and the server responds even if there's no new data. Latency. Since requests are sent at fixed intervals, there can be a delay if new data arrives just before the next scheduled request. Unsuitable for applications requiring real-time updates. Suitable use cases. Applications with low real-time requirements, such as systems with infrequent updates or simple notification systems. Long polling improves upon short polling. After the client sends an HTTP request, the server doesn't immediately respond. Instead, it keeps the connection open until there is new data to send. If no data is available within a certain time frame, the server responds with an empty message, prompting the client to issue a new request. Essentially, the polling frequency is reduced and the server only responds when there is data available. Advantages: improved real-time performance. The client receives server updates more promptly, achieving shorter latency than traditional polling. Reduced resource waste. Fewer unnecessary requests are made compared to short polling, as connections are maintained but data is only sent when available. Disadvantages: higher server load. Since the server holds many open connections, resource use can become a concern, especially with many concurrent requests. Implementation is more complex, requiring server optimizations to support prolonged connections. Suitable use cases: applications needing moderate real-time updates, such as social media notifications or instant messaging. It is more efficient than short polling, but still lags behind WebSockets in real-time performance. WebSocket is a TCP-based bidirectional communication protocol that allows persistent, full duplex data exchange between the client and server over a single connection. Unlike traditional HTTP, after a WebSocket connection is established, both client and server can send data to each other without needing to re-establish HTTP requests. Advantages: strong real-time performance. As a full duplex connection, the server can push updates to the client in real time, and the client can also send requests instantly. This makes it suitable for applications requiring high real-time responsiveness. Low latency. Once the connection is established, there is minimal delay in communication, unlike polling, which repeatedly opens and closes connections. Reduced bandwidth consumption. Compared to polling, WebSocket reduces the cost of repeated connection setups and lacks the overhead of extra HTTP headers, thus conserving bandwidth. Disadvantages: complex implementation. Both server and client must support the WebSocket protocol, and maintaining the connection requires handling complex resource management, including connection heartbeats and reconnection logic. Not ideal for short-term connections. WebSockets are designed for persistent connections. For short-lived or infrequent requests, the overhead of establishing and maintaining a WebSocket connection can exceed that of traditional HTTP. Suitable use cases: applications with high real-time and concurrency requirements, such as stock trading platforms, online gaming, instant messaging, and real-time collaborative applications. In summary, short polling is suitable for small applications with low real-time requirements. It is easy to implement, but has low resource efficiency. Long polling fits applications with moderate real-time needs. It reduces unnecessary requests, but increases server resource usage. WebSockets offer the highest real-time performance, ideal for high real-time, high concurrency scenarios, but require higher implementation complexity and resource management.
Thanks for watching. For more information, please visit bowsier.com. CDN, Content Delivery Network, is a distributed network system primarily designed to accelerate the delivery of static content, reduce server load, and improve user access speed and experience. By replicating content across multiple geographically distributed server nodes, CDN enables users to retrieve content from the node closest to them, thus enhancing access speed and reducing latency. The core principle of a CDN is to cache content across multiple globally distributed servers, called edge servers. When a user requests a resource, the CDN automatically delivers it from the server closest to the user instead of fetching it directly from the origin server. The detailed process is as follows. 1. User request. When a user accesses a website or application, it first sends a request for resources to the DNS server. 2. CDN routing. The DNS server, based on the user's geographic location, routes the request to the nearest CDN edge server. 3. Cache lookup. The CDN edge server checks if it has the requested content in its cache. On cache hit, if the content is cached, the CDN directly returns the cached content, providing a fast response for the user. On cache miss, if the content is not cached, the edge server requests the resource from the origin server, then caches it for future requests. 4. Content delivery. The user receives the content from the cache rather than the origin server, reducing load and latency. Advantages of CDN are: 1. Improved access speed. With CDN nodes distributed across multiple regions worldwide, user requests can retrieve resources from the geographically closest node. This reduces latency and response time, enhancing the user experience. 2. Reduced server load. By distributing content across multiple edge nodes, CDNs decrease direct access to the origin server, dispersing traffic loads and reducing the risk of server downtime. 3. Bandwidth optimization. Through caching and compression, CDNs minimize data transfer volumes, optimizing bandwidth usage and saving costs. 4. Increased availability. Due to the distributed nature of CDNs, even if certain nodes go down, other nodes can still serve content, ensuring high availability and fault tolerance. 5. DDoS protection. CDNs help mitigate DDoS attacks by dispersing traffic loads, protecting the origin server, and enhancing security. Disadvantages of CDN are: 1. Content update delays. Since CDNs rely on caching, if content on the origin server updates, but the cache doesn't refresh promptly, users may receive outdated content. 2. Complex cache configuration. For dynamic or frequently updated content, configuring CDN cache strategies effectively can be complex and may lead to cache invalidation issues. 3. Cost. While CDNs optimize bandwidth and reduce server load, they may add extra expenses, especially for smaller websites or applications. 4. Geographic dependency. If CDN edge nodes are sparse in certain regions, user experience in those areas may not improve significantly. Some CDN examples are: 1. Video streaming sites. Platforms like YouTube and Netflix rely on CDNs to distribute video content quickly, ensuring smooth streaming experiences for users worldwide. 2. E-commerce. Platforms such as Amazon and Alibaba use CDNs to improve page loading speeds, allowing users to browse products and place orders efficiently. 3. Social media. Social media platforms like Facebook and Instagram utilize CDNs to deliver large volumes of static resources, such as images and videos, ensuring seamless access for users globally. 4. Game distribution. Gaming platforms like Steam and Epic Games use CDNs to distribute large game installation files, boosting download speeds and reducing server load. Thanks for watching. For more information, please visit bowsiate.com.
ACID represents the 4 essential properties in a database management system, DBMS, that ensure transaction reliability, atomicity, consistency, isolation, and durability. Together, these properties ensure that when executing transactions, the database maintains data integrity and reliability, even in the event of system failures. Atomicity ensures that a transaction is either fully completed or not executed at all. Partial transactions are not allowed. All steps in a transaction must either complete entirely or be entirely undone. Example: in a bank transfer, if Alice transfers $100 to Bob, the transaction includes 2 steps: deducting $100 from Alice's account and adding $100 to Bob's account. If an error occurs midway, the transaction rolls back to ensure neither step occurs. Consistency ensures that a transaction moves the database from one valid state to another, maintaining all integrity constraints. Before and after a transaction, the data must be in a valid state. Example, for Alice and Bob's transfer, if the total balance across both accounts is $1,000 before the transaction, it should remain $1,000 after the transaction, regardless of success or failure. Isolation ensures that multiple concurrent transactions do not interfere with each other. Transactions should appear as if they are executed sequentially to prevent reading intermediate, uncommitted results from other transactions. Example, while Alice's transfer is in process, if Bob checks his balance, he should only see the final result, not any intermediate state, ensuring he does not see the deduction from Alice's account until the transaction is fully complete. Durability guarantees that once a transaction is committed, its result is permanently saved in the database, persisting through any system crashes or hardware failures. Example, once Alice's transfer is successfully completed, her and Bob's updated balances will remain intact even if the system crashes right afterward, ensuring the transaction's results are retained. Here are some popular databases that support ACID properties. MySQL is an open-source relational database management system, and its InnoDB storage engine supports ACID-compliant transactions, ensuring data reliability and integrity. PostgreSQL is an open-source relational database known for its strict adherence to ACID properties, making it suitable for applications that require high data consistency and reliable transaction handling. Oracle is one of the most widely used commercial databases, providing robust transaction management and full ACID support, often chosen for high reliability requirements like financial systems. SQL Server, Microsoft's enterprise-level relational database, offers comprehensive transaction support and adheres to ACID standards, making it ideal for data applications that require high reliability and consistency. IBM DB2 is a relational database management system by IBM, supporting ACID properties and widely applied in critical industries like finance and telecommunications. Thanks for watching. For more information, please visit bowsier.com.